When we look at the universe, it is common to feel that we are very small compared to it. The feeling worsens when we remember how little we know about our own universe. We are curious by nature, so it is natural that every civilization throughout history has wondered what the universe is. Why is there something instead of nothing? How did everything come into being? And currently, various fields of science are trying to answer these questions, each using its own tools and approaches.
Hey, Pedro here. This video you are watching was originally in Portuguese, my native language. This is the attempt of our team to translate it to English, and I sincerely hope you enjoy it. Your feedback is extremely important to us. Now, back to the video.
But when we talk about understanding the phenomena of the universe as a whole, one area stands out: physics. Physics is one of the sciences that tries to explain what we observe, and using mathematics allows us to develop equations that describe what we see. We can predict the speed at which galaxies move away from us just by knowing their distance from us, or the probability of an electron being in a certain location. But even physics is divided into areas that deal with different scales. Most of the things in our daily lives, such as boiling water or a moving car, are described by classical mechanics. But as we start dealing with higher speeds, increasingly closer to the speed of light, classical mechanics lets us down. It cannot explain particles with very high speeds, which even have a special name: relativistic. Photons, which are the particles of light, are a perfect example of this. That is why we need relativity, which is another area of physics, because it is only through it that we can explain these fast phenomena. And even relativity is also divided into two: special relativity and general relativity. Special relativity focuses much more on speeds close to the speed of light and with weak gravitational fields. General relativity, on the other hand, focuses on intense gravitational fields where special relativity has problems. And here I need to make one thing very clear. When we talk about low speeds and a weak gravitational field, like that of the Earth, relativity gradually converges to classical mechanics. That is why we can use Newton's laws to describe cars and airplanes. But there is a third area that deals with the smallest known scales, and this area requires a lot of attention: quantum mechanics. It is impossible to try to understand what happens in the quantum world, at the smallest scales, using the mindset of classical mechanics. At such small scales, probabilities dominate everything. The deterministic world we are used to no longer works. Okay, so general relativity arises when we are talking about intense gravitational fields, which classical mechanics does not explain. And quantum mechanics arises when we talk about particles and interactions at the atomic scale. But what if we have a situation where we are dealing with scales smaller than an atom, and along with that, an intense gravitational field? Putting it another way, a situation where we need both quantum mechanics and general relativity at the same time. This something exists, and you will understand if you watch this video until the end. But first, let's take a few steps back and talk again about the limits of each area. As I just mentioned, classical mechanics or classical physics breaks down when we deal with very high speeds or very intense gravitational fields. But what about quantum mechanics? Does it always work? The answer is no, or this video wouldn't exist. Quantum mechanics successfully explains three fundamental interactions: weak, strong, and electromagnetic. But there are four fundamental interactions in total. Here, the gravitational interaction was missing. And in fact, quantum mechanics breaks down when we introduce gravity. Infinities begin to appear, divisions by zero emerge in the equations, and things cease to make physical sense. It is almost as if quantum mechanics does not accept gravitational interaction within it. And from the point of view of relativity, which is the tool we use to describe gravity, something similar happens. Using the equations of general relativity for very small regions of the atomic scale causes divisions by infinite zeros to also start appearing. And in physics, when we encounter divisions by zero and it is impossible to avoid them, it usually means that we have reached the limit of our field. This is very curious because then we have two successful areas of physics failing at exactly the same point. But why? Could it be that quantum mechanics and general relativity do not work together because there is nothing that requires both the atomic scale and intense gravitational fields at the same time? The universe itself might be trying to tell us something because it has given us a region where we have exactly that happening: singularities. Singularities are regions of the universe where all our best theories of physics seem to fail, and they are extremely important for understanding the history of our universe. They are inside black holes, and the Big Bang itself was probably initiated from a singularity. We still haven't managed to make quantum mechanics and general relativity work together to explain singularities. The solution is still unknown, but it has a name: quantum gravity. Quantum gravity would basically deal with the extreme of both areas in situations where neither provides concrete answers. It would also be related to the unification of physics, which is the goal of combining the four fundamental interactions. It's as if quantum gravity were one of the most important pieces for us to get closer to completing the immense puzzle that is physics. Finding a good theory for quantum gravity would be an advancement as significant as Newton's laws or relativity. It would allow us to answer questions such as what happened in the first moments of the Big Bang and what exists inside black holes. There is only one problem. What is quantum gravity? We know the main condition is it would need to agree with both relativity and quantum mechanics. But how would this be done? The person who finds this answer will probably win a Nobel and be marked in history alongside names like Einstein and Marie Curie. Einstein himself spent decades of his life focused on trying to find this answer, and several other great names in physics, such as Stephen Hawking or Erwin Schrödinger, also tried to contribute with answers. So the question we need to answer now is, considering the number of physicists who have worked on this issue, how close are we to quantum gravity? Let's look at some of the best ideas we have at the moment. String theory is the most famous among all the proposals for quantum gravity. At first, it even seems like a simple idea, but only at first. Let's suppose that, instead of dealing with particles behaving like points, which would be the description of quantum mechanics, we are going to deal with strings. And these strings are very small, and they vibrate at certain frequencies depending on the particle or interaction being described. Electrons would vibrate in one way, photons would vibrate in another, and bosons in yet another, and so on. Each particle in interaction known by the Standard Model would actually be a vibration of these strings. The theory even predicts a vibration for a particle called the graviton, which would be a manifestation of gravitational interaction. The existence of the graviton has not yet been confirmed, and we even have considerable difficulty incorporating it into the Standard Model of particles. But in string theory, this would be possible, and then we could achieve the long-dreamed unification of interactions. String theory is truly magnificent from a mathematical point of view. There's just one catch. One of its major problems is the existence of more dimensions. Some descriptions go up to 26 dimensions in total, and the most famous one has 11 dimensions, 10 spatial and 1 temporal. And this is practically 3 times the number of dimensions we know to exist through general relativity. So, how could string theory combine general relativity with quantum mechanics if they don't even work with the same number of dimensions? Most of the current work in string theory is trying to find ways to pack the extra dimensions into each other, until we arrive at the 4 dimensions we are accustomed to. But I don't need to say that this hasn't been easy. And another major criticism of string theory is that we have not yet reached the technological point where we can observe and test the theory's predictions. Some physicists even suggest that these tests would be impossible. And that is why, in physics, string theory is not even considered a theory, despite the name. It is more like a hypothesis. But today is our lucky day, because it is not the only proposal for quantum gravity that we have. I know this is going to sound strange, but the other proposal I'm going to talk about now has practically the same name, loop quantum gravity. While string theory focuses more on the aspect of quantum mechanics, loop quantum gravity focuses more on the aspect of general relativity. The great differentiator of this idea is that the fabric of space-time is no longer continuous, as we imagine in general relativity. It now has discrete values. And one way to visualize this is to imagine space-time as being formed by many small pieces, much like a patchwork quilt. The small pieces would make connections and form a kind of network, or using the correct term from physics, space-time would be quantized. And it is these connections, along with the properties of each of them, that would create what we know and experience as gravity. And even better, the properties we expect from quantum mechanics would also be explained within these small loops and connections. The good thing about this idea is that we can achieve all this without invoking the existence of more dimensions. But all of this seems too perfect. So perfect that some researchers criticize this description, saying that it ignores important properties of quantum mechanics. Another common criticism comes from researchers who say that this proposal is just a more embellished general relativity. In the end, loop quantum gravity falls into the same problem as string theory. We have no way to conduct experiments and observations to prove it. And this brings us to the most curious proposal, which originated in relation to string theory, the holographic principle. In the holographic principle, the idea is that all information and phenomena in a volume can be represented on an area that encompasses that volume. In a simplified way, imagine that the universe is the inside of a balloon, but all the information about what is happening inside is encoded on the surface of the balloon. The holographic principle suggests that gravitational effects we see and experience in our three-dimensional world can be described by a two-dimensional world without gravity. And this might be one of the most innovative and curious approaches to the problem of quantum gravity. If gravity is a problem, then why don't we just make it disappear? Jokes aside, the holographic principle considers what we know about gravity through general relativity to explain what we observe in 3 dimensions or 4 if we consider time. And often this principle arises as a solution to problems associated with black holes, such as the famous information paradox and even singularities. But this raises a question. If after all this effort we still haven't arrived at a satisfactory answer, is this pursuit worth it? The answer is yes, because it would help us solve important problems like singularities and bring us one step closer to better understanding the universe we live in. Every effort is valid in basic science research such as quantum gravity. And a perfect example is electromagnetism. 200 years ago, we knew practically nothing about it. It was the curiosity of physicist Michael Faraday that served as a trigger for other great names, such as Maxwell, to become interested and develop equations that explain the phenomenon. And today, centuries later, you are watching this video on a device that only works because we understand electromagnetism. Society changed completely with the introduction of electricity into our lives. Want another example? If Marie Curie had not dedicated her life to better understanding a phenomenon called radioactivity, we would not have cutting-edge medical exams today. The truth is that we still cannot say that we completely understand gravity, even with the advances that Newton and Einstein have made in our understanding. And that is the beauty of the pursuit of knowledge. We never know where it will take us or what amazing things we will discover as a consequence. That is why we always need to strive to go further and ask more questions rather than wait for answers. But I would like to hear from you. Which of the theories about quantum gravity is your favorite, and why? Type here in the comments. Thank you very much and see you next time.